Our world is this massive, tangled web of cause and effect. Think about it. A doctor's trying to make sense of conflicting test results. An investor is just staring at a market chart that's going haywire. A meteorologist is trying to guess where a storm is going to hit. We are constantly forced to make these huge decisions with, let's be honest, not nearly enough information. The world is random, but your decisions really shouldn't have to be. So, what if you had a clear, visual tool to cut through all that uncertainty? A kind of mathematical key to unlock these super complex problems? Well, that key actually exists. And today, we're diving deep into what they are: Bayesian networks. So here's the fundamental challenge, right? It doesn't matter if you're a data scientist or a doctor. The big problem is trying to make sense of a world where everything feels connected, but all those connections are foggy. We've got bits and pieces of information, sure, but how do they all influence each other? The answer isn't just about getting more data, it's about finding a whole new way to see the problem itself. Okay, let's really look at this thing. At first glance, it just looks like a simple chart, right? But this is a Bayesian network, and it literally turns all that chaos we were talking about into a clear, logical map. Just notice how the chance of rain and whether the sprinkler is on both directly influence if the grass is wet. And that, in turn, affects the road conditions. It's an incredibly intuitive, visual way of modeling how things in the real world actually work. And listen, this isn't just some static diagram you draw on a whiteboard and forget about. No way. This is a dynamic engine for reasoning. Bayesian networks are used in a surprising number of fields to really get a handle on probabilistic thinking and deal with that messy real-world uncertainty. We're talking about predicting medical diagnoses, modeling stock market risk, and even something as common as deciding which of your emails is actually spam. So, the big question is, how are these powerful maps actually put together? To build one, you basically need two key ingredients: a blueprint that lays out all the relationships, and then the mathematical muscle to bring those relationships to life. This pyramid is a great way to see how a network is built from the ground up. Right at the bottom, we have our basic building blocks. These are the random variables, or what we call nodes in the graph. As we move up, we add the structure that connects them all together. And finally, we put in the numbers that quantify those connections, creating a complete model of the entire system. So that structural layer, it's got a technical name: a directed acyclic graph, or just DEG. But the easiest way to think of it is as the skeleton, or the blueprint for the whole network. The nodes, those are the variables we care about, like rain or sprinkler or wet grass. The arrows, we call them edges. They show direct influence. Rain causes the grass to be wet. And that word acyclic, it's just a fancy way of saying an effect can't loop back and cause itself. Simple as that. Now, if the DAG is the skeleton, then the conditional probability tables, or CPTs, are the muscles. This is where we start attaching hard numbers to all those arrows. For every single node, a CPT answers the most important question. Okay, given its causes, how likely is this effect? So for example, a table might tell you there's a 90% chance the grass is wet if it's raining. This is where the network gets all its predictive juice. So we've built the structure, and we've given it muscle. Now let's see how it actually works. I mean, having the map is one thing, but using it to navigate is where the real magic happens. This whole process is called probabilistic inference. It's basically how the network thinks. This flowchart here shows you the whole process in action. When we get a new piece of information, when we observe some new evidence, the network runs what's called an inference algorithm. This automatically updates its beliefs about everything else in the system. It calculates all the new probabilities for the things we don't know based on the one thing we do know. Let's just walk through a super simple example. Step 1, you wake up, you look outside, and you observe the grass is wet. That's your new evidence. Step 2, the inference algorithm kicks in and starts running. Step 3, the network updates all its beliefs. The probability that it rained, that goes up. The probability that the sprinkler was on, that also goes up. Finally, step 4, you can ask the network a direct question. Hey, given that the grass is wet, what is the new likelihood that it actually rained? So, here's the really crucial point. This isn't just for some backyard weather prediction. This ability to reason with uncertainty has world-changing applications across just a ton of different fields. So, let's take a look at where these networks truly shine. The breadth of the impact here is just staggering. In medicine, they're helping doctors untangle really complex symptoms to find the most likely disease. In finance, they're modeling the cascading effects of market shocks. A robot uses them to fuse data from its cameras and its sensors to build one coherent picture of its surroundings. From detecting subtle cyber attacks to helping us build safer AI, Bayesian networks are a core engine of modern prediction. But of course, no tool is perfect, right? The huge strength of Bayesian networks is that they are transparent. Unlike a lot of black box AI models, you can actually follow their logic, which is absolutely critical in fields like medicine. They also handle uncertainty beautifully. Now, on the other hand, automatically learning the structure from data can be pretty slow, and those probability tables can get enormous for really complex problems. And it's important to know they can't model systems that have feedback loops. And that brings us to our final thought. We've seen how these networks can model everything from medicine to markets just by mapping out these hidden probabilistic relationships. So the question I want to leave you with is this. If you could apply this kind of clear, structured reasoning to any complex system in your world, what's the first problem you would try to solve?